Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture on control systems. So we have been discussing this contour mapping over this last lecture, which is supposed to lead us to this important topic called Nyquist criteria, right. So we have seen how if you have a contour chosen in the Argand plane, that is the complex plane, yeah, we have seen how it maps to another contour in the FS plane. So basically the idea was that, as we pointed out earlier the other day, right. So if you have a contour in this complex plane here, as you can see, and you pass it through every point on this contour S1, S2, S3, you pass it through a function and you plot it on the function plane. So the real part of Fs and the imaginary part of Fs are the x and the y axis respectively in that plane, right. And you see that a contour here will lead to a contour there, but more importantly what we did observe was that if you had a pole or a 0 inside this contour in the Argand plane, yeah, then that leads to some interesting behavior in the FS plane, in the sense that if the pole is not encircled or included inside this contour, this closed curve, right. So before that, let me just remind you that of course this contour has been chosen in the Argand plane in such a way that at no point do you encounter difficulties in plotting, that is, it is analytic, okay, it does not blow up at any point. So you do not encounter the poles at any point on the contour, it is either completely inside or it is completely outside, it is not at the boundary of this contour. Yeah, so that is a critical aspect that you have to bear in mind. Now what we did observe was that if the pole is inside and if the pole is outside, there is a crucial difference in the fact that either the origin is encircled or it is not. Also in addition, the same thing carried over for a 0 as well. Yeah, we have seen that the same thing carried over for a 0, right. So if you have the 0 inside, then it is one kind of a contour you get here, that is this, right, and if you have the 0 outside, then it is quite a different kind of a contour that you would get, right. Yeah, so that is basically the take home message from this. And then we ended the last lecture by seeing what if there is one pole and one 0 inside this. And we saw that in such a case, even though you have one pole and one 0 inside, so earlier the other day we saw that if you have just one pole or just one 0, then the contour in the FS plane encircled the origin. But if you have like a pole and a 0 inside, then there is kind of like a nullifying effect of the two, and in the end what you have in the FS plane is a contour which does not encircle the origin at all. Of course, depending on the relative location of the pole and the 0, the sense of the contour can be plotted, but then it is not of much interest to us, because the crucial aspect that we were looking for is how many times does it encircle the origin, and we saw it is 0. And we illustrated this geometrically. We showed you that eventually this angle, the phase, so it is basically principle of arguments, which is angles, right, of complex numbers. So if you have one pole and one 0, then this angle, the difference is given by this angle in this triangle, right. So let me draw that a little larger here. So if you have this emanating from a pole and a 0 like this, so if this is from a 0, this is from a pole, yeah, then the net angle difference, this angle is equal to nothing but this angle plus this angle. So therefore this angle minus this angle, yeah, so this minus this will lead to this angle, yeah. So this is basically theta p, this is theta z, and this is theta p minus theta z, right. So essentially we saw that if you have to have a negative real crossing, then this angle has to be 180 degrees, and if this angle has to be 180 degrees, then their contour must pass through this part of the real line joining these pole 0 pair, joining this pole 0 pair. So therefore you must have such a nasty type of a contour. In general, the type of contour I had chosen did not have that feature, and therefore the question of even going as far as 180 degree did not arise, and therefore it was easy. But now we will be interested in this question a little more. You see, I told you the other day that from this figure it's as if obvious that there is no encirclement of the origin, and you would also believe me because you say that there is a way to go towards infinity in one particular direction where you don't encounter this contour at all. So in some sense it's free to move out. It's as if you are located at the origin, and if you want to walk out avoiding that contour, say that's like a forest in a map, and you want to avoid the forest and you want to bypass, go around it, you can find your way around it. Yeah, you can go around, go to any point except within that forest, you can go to any point by finding your way around this contour. So you would believe me if I said that this actually depicts no encirclements. Now unfortunately, when you get to a larger number of poles and zeros inside, this sort of notion of encirclement, or this straightforward notion of encirclement, does not hold. So if you have to count the encirclement, a more sophisticated notion is required, which is the so called test radius or a test phasor. What do I mean by that? So consider something like this. Suppose this is the origin, and you have a curve drawn around the origin that looks something like this. Okay. So suppose this curve, it doesn't look like a very nice curve now, does it? Yeah. So you see, this is the curve here, this is the curve here, and this is how it goes, right? Now here also, if you think about this notion of escape from the origin without touching this contour, you will see that you can trace your way out of this by traversing in this direction and then going anywhere. Yeah, you can go anywhere out. But then how do you keep doing this? This is not a very efficient way to check for encirclements, right? So one way to do that is, we say that you draw a test radius in any direction. Yeah, draw a test radius or a test phasor starting from this point. This is the origin, the critical point that I am interested in. And then I see how many times I am cutting across this periphery of this contour. So you see, in this blue line here, it cuts across the periphery of the contour twice. So does that mean the encirclements is 2, number of encirclements is 2? Well, no, and that is the crucial bit. You see, the first time you cross this periphery, you see that this crossing is on the counterclockwise direction. The second time you cross, you see the crossing is in the clockwise direction, and they will cancel each other out. So it's like you've actually passed through the forest, yeah, but you've gone in and you've also come out of the forest, right? So therefore the net encirclements is going to be counted as 0. So it turns out that you don't always need to necessarily look for an opening or a path like this to escape and then understand that there is no encirclement. The simplest way to check for an encirclement, of course, in the case of 1 pole and 1 zero, it was very easy, because you see that it's obvious to see the kind of contour I chose here. It's very obvious to see that this point is not encircled. We understand this encirclement notion intuitively itself. But if you get really complicated sort of contours, such as the one I have drawn here, yeah, this intuition might not always be very straightforward and obvious. So what you then do is you draw this test radius or a test phasor, and you see how many times it cuts across this contour, and then you count the sense in which it is cutting across this contour. So you see here it's counting, it's going anti-clockwise, counterclockwise, here it's going clockwise, so they have a nullifying effect. So the net encirclements is going to be 0 even about this point, which is again, as I said, in line with our understanding that there is a way to escape from this without going through this forest. So that is an important notion, how to know, what is this idea of encirclement. Yeah, it's easy to check if you have this idea of a test radius or a test phasor in mind. With this at the back in our kitty, this particular tool or way of seeing things, we shall now look at the more general case. So for instance, you have, let's say, a pole pair here, a 0 pair here, another pole here, and another 0 here, right? And suppose I decide to choose a contour such as this. So this is again something in the Argand plane, yeah. So I choose this particular contour. Again, as I always do, I am going to choose it in the clockwise direction, yeah, and I want to understand what is going to happen in the Fs plane. So this is the real part of Fs and this is the imaginary part of Fs. So I am not going to draw this because you see I do not know whether it is going to be a complicated shape like this, right. I want to get an idea based on my understanding of this notion, of this principle of argument. And what does the principle of argument tell me? You see, cast your attention back to a typical transfer function that we considered, such as this. The important thing to remember here is that you see the net argument or the angle of this function Fs is the sum total of the contribution of those individual blocks, right. Everything on the numerator, those 0 blocks, they get added, and everything in the denominator, the pole blocks, they get subtracted from there. It is just like division and multiplication of complex numbers, that is all there is to it, right. Now, using the same idea and trying to push forward with it, what do we see here? Suppose you call this your P1, P2, P3, Z1, Z2 and Z3, right. Now you take some test points here and you see what is happening. Of course, if you want to really plot, then you will need these exact numerical values here. So you see this is the phasor here, this is some phasor here, this angle, and this is some phasor here like this, so this angle, yeah. So you have to sum total these angles and you have to see, so this is some positive angle, maybe some 20 degrees, this is some 170 degrees maybe, and this is maybe some 100 degrees. So 170 and 100 minus 270 because it is in the pole, so it is basically 20 minus 270 degrees, yeah. So it is going to be like minus 250 degrees. So minus 250 means it is going to be in the clockwise direction, so it is 180 and 250 would be somewhere here. So this point S1 will probably map somewhere here, I do not know the magnitude, yeah. So you see immediately you realize that it is kind of hopeless to try and draw this plot for a general case, right, how large this magnitude will be, and in fact we do not even care about the magnitude. After all, as I said, this entire Nyquist criteria is dependent on this principle of argument. So then what are we going to do about this, or how are we going to get an idea about how many times this plot is going to encircle, how are we going to convince ourselves that how to interpret this or read this off, because clearly this reading of this even this 20 degree thing I just assumed arbitrarily. I have not been able to give conclusive evidence of what the kind of configuration will be. So you see, unlike with the one pole 1 0 case where I really know this relation between these two angles, which is basically nothing but the third angle in this triangle I have constructed, here the moment this pole and 0 increase, it will give you some polygonal sort of shape inside, and it is really very complicated to get the geometric insight. So the way to see this is, you look at this entirety of this contour, and once you have travelled across this entire contour, you see for any point inside this contour, the net phase change of the phasor emanating from that point and joining points on this contour is, you go once around, right. So you go once around for every 0, so for every 0 it is a net change of 360 degrees. For every pole also it is a net change of 360 degrees, but it appears in the denominator. So instead of being clockwise, it happens in the counterclockwise direction for every pole inside it. So therefore, I am going to just write the net contributions, okay. I can do that because I can add the arguments of complex numbers when they are in the product form, right. So what happens? So Z1 contributes plus 360 degrees, P1 and P2 will contribute minus 360 and minus 360, so that is minus 720 degrees, yeah, overall, okay. So note that, so this is crucial, do not get confused about this, it might appear a little confusing. What I am saying here by plus 360 does not mean that it is a counterclockwise plus 360, that is the convention we generally adopt here. So later on we will again change this, so that is where people mostly get a little confused. when I am plotting this here and I am trying to find out the net contribution, when I write plus 360, what I essentially mean is that it agrees with the orientation of the contour in the S plane. So the orientation of the contour in the S plane is clockwise, yeah, it's rotating clockwise. So when I am saying Z1 contributes plus 360 degrees, it means that in the FS plane, Z1 will contribute a clockwise full encirclement, okay. What about P1 and P2? When I am saying they are each contributing minus 360, it means that they are all going to contribute a minus 360 degrees, so a counterclockwise rotation, yeah, so that's minus 720. What about points like P3, Z2 and Z3? That we have already seen. You see, when you try to trace this path, it goes once like this, increases, then again it starts decreasing, so it just goes to and fro, yeah. The first time you start from here, you go in this direction, yeah, so the phasor goes in this direction up until this point, and then again it starts reducing from this point onwards, and it goes like this, reduces, then again it goes here, it's like oscillating. So if I plot the phase function of this across, as this goes across this contour, yeah, I'll have some oscillating nature, but it will never really go and make one full 360 degree. Same argument holds for Z2 and Z3. So basically P3, its net contribution is 0 degrees because it's outside. Same contribution for Z2 and Z3, it's 0 degrees. So if I sum total all of this contribution, the sum is minus 360 degrees. So this minus 360 degree, what does this minus sign tell me? Minus sign tells me it is in the opposite sense of the contour in the argand plane. So what is the sense of the contour in the argand plane? It's clockwise. So in the FS plane, the contour will have a counterclockwise net encirclement, one net encirclement. But what is this 1? Why is this number 1 significant? You see, the number 1 is basically the difference between the number of poles and the number of zeros inside the contour, and here is where we have this interesting and important result on which the entire principle of Nyquist criteria hinges. What does it say? So suppose I have n poles and m zeros inside a contour, zeros of what? Of Fs, inside a contour in the argand plane, which is the complex plane, then the corresponding contour mapped in the Fs plane will have n minus m net counterclockwise. So of course inside a, so let me make this clockwise, because this is the convention we will always choose. We will always choose a clockwise contour in the argand plane. If you make it to counterclockwise, everything, everything can be translated. It's just a convention. We don't want to make things too complicated. Yeah, you can also choose. Some textbooks also consider counterclockwise contours, in which case things will just change. You just give it a moment's thought, it will be clear. So we chose a clockwise contour in the argand plane. In that case, there will be a net n minus m counterclockwise encirclements of, so then the corresponding contour mapped in the Fs plane will have n minus m net counterclockwise encirclements of the origin, of course, of the Fs plane. Yeah, you are mapping it in the Fs plane, so it is the origin of the Fs plane. So that's the net conclusion. So now you see, you can have a negative number of counterclockwise encirclements. Negative number of counterclockwise encirclements means just you remove the negative sign and that many clockwise encirclements. Yeah. So because this sense is what we are considering, this counterclockwise and clockwise, that's why having a positive or a negative sign makes sense. Normally you might think, what is this idea about bringing in positive and negative sign to this encirclements? The positive and negative sign comes in because of the sense in which you are counting the encirclement. So normally we count the encirclements, so we choose the contoured, crucial bit. If you adopt this convention, stick with it. Crucial bit is choose the clockwise contour in the Argand plane, count the number of counterclockwise encirclements in the FS plane, right, and that will tell you what. So basically, in summary, number of net counterclockwise encirclements of the origin in the FS plane, of the origin in the FS plane is equal to, here is the summary of what we have discussed, is equal to number of poles of FS, yeah, minus number of zeros of Fs. Of course, what I have not written here, but I am going to add now is number of poles of Fs where? Number of poles of Fs encircled by the contour in Argand plane, and this is of course the number of zeros of Fs encircled by the contour in the Argand plane. So that is the crucial bit, yeah, it is not just the total number of poles minus the total number of zeros, yeah, you are choosing a contour in a special way to enclose or encircle a certain number of poles and zeros of this function Fs inside it, and then you can talk about the net number of encirclements of the origin in the Fs plane being equal to the difference between the number of poles of Fs and the number of zeros of Fs, okay, assuming that you are counting it in the counterclockwise sense. So this is the most important thing you learn about the Nyquist criteria, and if you do well to remember this, at no point should you face any problems, okay. So often people confuse with this and then things start going downhill from there, yeah. This is the summary. So now you might wonder what all this has to do with this notion of stability, and this is arbitrary contours we are drawing on this Argand plane and stuff. We are also taking arbitrary type of Fs functions apparently, okay, maybe some properties that this function Fs has, which of course I have not spoken about, but I mean, how does this help us in our answering our question? Something akin to this Routh-Hurwitz criteria, or something that we could see clearly from this root locus technique. Can we at all make use of this result that we have just seen in the previous slide to deduce something similar along those lines about the stability of a closed loop, yeah, from the open loop transfer function? It turns out, by a very smart choice of this contour, yeah, this is exactly the thing we are looking for. This tool that I have just mentioned here is exactly what we are looking for. So what sort of a contour shall we choose? I mean, I have shown you that there can be nasty kinds of contours and all sorts of plots and things like that. What is it that makes sense for us to choose? So for that, just think, what is that forbidden forest for you, where you must not go, right? The forest of Fanghorn. Insofar as stability is concerned, we must never allow our poles and zeros to venture into the right half plane. So of course this forest is in the Argand plane, not in the Fs plane like I mentioned earlier. So you see, you do not want your poles and zeros to be on the right half of the complex plane. So is there a way that I can choose a contour that includes the entirety of this right half plane? Seems like a daunting task, for the simple reason that it is an infinite area, right? That region never ends, it goes till infinity on half the space, right, half the plane, right, on any direction between minus pi by 2 to pi by 2 if you head, yeah, you can keep going on and on, starting from the origin, you go along any direction from minus pi by 2 to pi by 2, yeah, any direction, and you will be on the right half plane, and you can go on walking and walking and walking, and you will always be on the right half plane. So it is an infinite region. Yeah, can we actually draw an infinite contour and make it still work? It turns out that it does, and that is precisely because of the kind of functions that we choose. You see, here is where these tidbits come in handy. So we will choose our fs to be of the nature such as this, I going from 1 through m, and s plus pi, I going from 1 through, or let me call this j, pj, j going from 1 through n, and the crucial detail that is important here is that n is greater than or equal to m. Why is this important? Why am I so hung up on this condition? You see, if n is greater than or equal to m, and if you let s tend to infinity, yeah, which is tantamount to basically venturing at an infinite distance from the origin on the s plane, the Argand plane, what happens to this function fs? If the denominator has a degree that is strictly greater than or at most equal to the degree of the numerator, because after all we are only dealing with rational functions when we are talking about transfer functions. So we are not going into complex analysis of general functions, we are only talking about the special class of functions that interests us in our course on controls. So what happens? If the degree of the denominator is greater than that of the numerator, you will see as s tends to infinity, along some direction or the other you will have a 0, yeah, because obviously if you let s tend to infinity, this is simple application of limits. You can just apply limits and divide the numerator and denominator by s to the power n, and if n is greater than or equal to m, you will either have a finite quantity if it is exactly equal to m, or you will have 0. So basically even if you have a contour that spans up to infinity, you do not have to worry about how to sketch this fs. All that you need to notice is that because you are dealing with at most strictly proper or biproper rational functions, that infinite contour is really not going to be of a big concern to us. Having already noticed this, now we go about making our choice of this contour like so. So let us say this is our, this is our Argand plane. So you can excuse me if I just sort of draw it like this, so it's going to look like this D, so of course this is, for my drawing it's going to be finite, but if you just stretch your imagination a little, you can think of this radius as infinite. So this radius r tends to infinity. So that is what it is, and of course, and in keeping with whatever we mentioned earlier, you will see that this is the sense in which we will consider this contour in the clockwise sense. So what we will do is, we will take test points on this contour, and we will plot them, we will pass it through this fs that looks something like this, and we will plot it here in the real part of f and the imaginary part of f, that is the f plane, and we will plot this contour here, and we will try to see what information can be extracted. So what is known to us? Well, we already know this pole and 0 locations if given in this factored form, so this is not of interest. What is of interest to us is, given an open loop transfer function, where do the closed loop poles migrate? Do they stay within the left half plane, or do they go to the right half plane for a certain value of k or a certain choice of parameters? That is our question. So just looking at this function is not very interesting. You can already see it is in the factored form. You can count the number of poles, count the number of zeros, and see how many of them are on the RHP and how many are on the LHP, and likewise you can already see how many times this origin will be encircled. This Nyquist is like, it's trivial, it's not interesting to us, it does not help us in understanding the closed loop behavior. So what are we going to do here? Now consider, now I am going to go back to this GS notation. So GS will have some NS upon DS form, where of course degree of DS is greater than or equal to the degree of NS. This is important because we only allow at most biproper or strictly proper rational functions to be our transfer functions. Now suppose you have this configuration, something that we are by now very familiar with. You have this controller and you have this plant, and then you have this unity feedback, right? You have this unity feedback, yeah, and this controller has maybe some parameter k and then s plus a upon s plus b, something like this, yeah, I do not know, something like this, and this also has some poles and zeros, right. This looks again something like s plus zi upon pi s plus pj. So, this is over j, this is over I, yeah. So, this is our plant and controller configuration. What we are interested in is, okay, for a particular choice of k, right, whether this is going to be stable. So, let us say our controller is given by NCS, it is also a rational transfer function upon DCS, okay. How does this help? Now, what is the closed loop transfer function? Let us just cast our attention to that. So, the closed loop transfer function is going to be GC upon 1 plus GC. Of course, I am omitting the S again for brevity, you understand it is there, it is a function of S, right. Now, notice that if I open this up a little more, this turns out to be N NC upon D DC divided by 1 plus N NC upon D DC. Yeah, so that means that this GCL turns out to be N NC upon D DC plus N NC, nothing new, we are already familiar with this form, yeah, we have done root locus analysis after all. So, obviously, this NC contains terms like this gain k. So, this gain k will be considered counted with this NC. Yeah, so it is not a monic polynomial in the numerator of the controller. Of course, it need not be a monic polynomial in the numerator of the plant either, but yeah, we can already absorb that gain. We can club together those two gains of the plant and the controller and consider them to be a single k. Yeah, because the plant gain is not going to change. The controller gain is what we have control over, which we can tune to our liking, right, and we want to understand if it is going to still lead to stable closed loop behavior. So, if we are now considering this closed loop transfer function, you see, what about this part? I want you to ponder over this little detail here. See, we got rid of this DDC in the numerator and denominator, and we could do that because it was common. Now, if you just think of the denominator of this GCL, so if you take the denominator of GCL, it turns out to be this 1 plus NNC upon DDC. This is itself another rational function, right. So, if you think of the denominator, this den GCL is equal to 0 will give us what? Will give us or rather solution of, if we solve for this denominator of GCL is equal to 0, this will give us precisely the closed loop poles. But we do not know what the closed loop poles are for different values of this gain k and these different choices, right. That is why we are invested in this question, that is what the root locus was all about. So, this is something we do not know, but what are these going to be like? So, this is tantamount to saying that DDC plus NNC is equal to 0 will yield the closed loop poles. But now, focus on this for a while, yeah, focus on this, because we are really going to consider this 1 plus C, 1 plus GC, okay, this is going to be our prime consideration. This 1 plus GC is nothing but exactly this, right. So, this is also, as I said, a rational function whose poles give DC, DDC is equal to 0, poles given by rather. So, the poles of this are given by DDC is equal to 0, or rather given by solving for DDC is equal to 0, and its zeros are given by solving for what? That is exactly what we were saying, this DDC plus NNC is equal to 0. So, in other words, and pay very careful attention, okay, this is again another juncture at which people sometimes get things messed up or confused. I started to investigate the question of closed loop pole location. In order to do that, I first wrote down the closed loop transfer function, which looked like this. Then I focused my attention on the denominator of the closed loop transfer function. Apparently, the zeros of the denominator of the closed loop transfer function, that is the zeros of 1 plus GC, will give me the closed loop poles. But interestingly, what about the poles of 1 plus DDC, or poles of 1 plus GC, sorry, those are going to be the zeros of DDC. And what are the zeros of DDC? They are nothing but the open loop poles, right. So, now instead of choosing this GCL or any of this, let me choose Fs, that general Nyquist function, is equal to 1 plus GC, okay. Then number of poles, or not number, then just the poles of Fs are the same as what? Look at this Fs, it is 1 plus GC. So, the poles of this are the same as the open loop poles. Of course, you might say the open loop poles of what? Open loop poles of G, no, open loop poles of GC, the entire block, okay. So, if you did not have this, if you cut this path, what you will have in the forward path is GC. So, it is the open loop poles of GC, not just G alone, yeah, because it is DC into D, right, it is not just D alone, the denominator of the plant alone, it is the plant plus controller, yeah. So, these are the open loop poles, yeah, and similarly the zeros of Fs, yeah, they are exactly the same as the closed loop poles. And this is beautiful. Why is this beautiful? Because now, just by looking at this open loop pole and the closed loop, I mean just by looking at the Nyquist contour, yeah, and mapping it on the Fs plane, yeah, this D that I had just shown you here, yeah, this D, and mapping it through Fs on this Fs plane, yeah, what do I need to do now? Look, what is known to me? This is known to me. This is known to me. So, apply the principle of argument. Now, therefore, on the Fs, which is of course equal to 1 plus GC, on the Fs plane, count the number of counterclockwise encirclements of the origin. So, remember what my contour was in this Argand plane, it was this D, yeah, the contour on the Argand plane was this D, alright. So, every point on this contour in theory, so bear with me a while, we will just shortly get into the nitty gritties of how to exactly plot this, okay, or get a rough qualitative idea at least on how to plot this. For now, you just believe me when I say that, yeah, this can be done. Of course, we have very sophisticated computers these days to help us with, yeah, in MATLAB we just type the command Nyquist and it will give you the Nyquist diagram. So, the point is that if you believe me that this is doable, So then suppose you kind of draw this, yeah, on the FS plane, then the conclusion that can be drawn is, on the FS plane, count the number of counterclockwise encirclements of the origin, say n, and as I told you, this n can be both positive and negative. So you are trying to count the counterclockwise encirclements. If you end up counting a certain number of clockwise encirclements, that is, then you just give it a negative sign. Yeah, and how to count this? Well, the plotting is the difficult part. Once you plotted it, then you just take the test radius or the test phasor. Yeah, so don't try to think of ways of winding around and finding an escape route and going around, right? Yeah, because that's cumbersome. So think of this test radius or this test phasor that you draw from this point, this origin, and see the net number of times this goes through. Okay, that will tell you everything that you need to know. So now, then what can we say? N is equal to what? Number of poles of 1 plus GC in RHP, because this contour, this D contour includes the entire RHP. That's by our design, by our very clever choice. Minus number of zeros of 1 plus GC in RHP, right? But what do we know about the poles of 1 plus GC? As we have already defined here, the poles of 1 plus GC, that is Fs, are nothing but the open loop poles of the system, and the zeros of Fs, that is 1 plus GC, they happen to be the closed loop poles of the system. Yeah, as we have already seen here, right, this 1 plus GC, you see it is nothing but D plus DC, I mean DDC plus NNC by DDC. So if you equate DDC plus NNC is equal to 0, that is going to give you precisely the closed loop poles. If you equate DDC to be equal to 0, that is going to give you precisely the open loop poles. So therefore I have this big claim now. So N, that is the number of net counterclockwise. So I am not going to talk about this repeatedly, like what the contour in the Argand plane looks like. Yeah, you already understand it is this D taken in the clockwise sense. So clockwise, okay, this clockwise D. At the heart of Nyquist is, every time you encounter a Nyquist, you understand implicitly that the contour in the Nyquist plane, the Argand plane, is going to be this D in the clockwise sense. Okay, so this is the net number of counterclockwise encirclements of origin in the Fs is equal to 1 plus GC plane. And what is this going to be equal to? This is going to be precisely equal to, notice, this number of poles of 1 plus GC in the RHP, that is going to be number of open loop poles of 1 plus, or sorry, number of open loop poles of the system in RHP minus the number of closed loop poles of the system in RHP. Yeah, so we have our result. In short, sometimes of course you might get again a little confused by the notation, but you see it will make sense when I explain it. In short, this is written as N is equal to this P minus Z, okay, P minus Z, but P is precisely this, yeah, the open loop poles, which are of course the poles of 1 plus GC, and Z is precisely this, the closed loop pole. So for stability, you want Z to be 0. So for stability, you want Z to be 0. Therefore, you want N is equal to P. That is it. So you just check whether N is equal to P. Okay, and if N is equal to P, then you have stability as you desire. Yeah. So if you have no open loop poles in the RHP, that is if the open loop system is stable, you do not want any encirclement of the origin, and that is mostly what people think. Yeah. But Nyquist does not tell you that it has to be 0, right. Nyquist tells you that the number of encirclements better be equal to the number of open loop poles of the system in the RHP. So sometimes people have this preconceived notion that no encirclements is better, or it's the desirable thing to happen, right. This is precisely the kind of thing that actually led to this initial confusion, when people thought like, how can decreasing the gain lead to instability and increasing the gain lead to stability from instability. Yeah. But you see, if your system is not open loop stable, in Nyquist it clearly and transparently tells you. So in the Bode plot you might have to see all those crossovers, phase crossover, gain crossover and stuff like that, and keep tab on all of those, right. But here it turns out it is not that difficult. The main difficulty is basically in sketching this Nyquist diagram. But once you have the sketch of the Nyquist diagram, you see, let me label this. Once you have the sketch of the diagram, this is known from Nyquist plot. So we call this sketch in the Nyquist, the sketch of 1 plus GC, the Nyquist plot. Yeah. And this is known from open loop transfer function itself. So the only unknown is this green. So this is the only unknown, like how many closed loop poles are there in the RHP, right. But here this Nyquist criteria, once you sketch this Nyquist plot, you know N, you know P, therefore you also know Z, right. So you know whether Z is 0 or not. If Z is not 0, then you know that the closed loop system is in trouble. It is an unstable closed loop system, alright. So that is the most crucial aspect of this Nyquist criteria, you have to remember always. Now all seems hunky dory, and there seems to be like no problem with this seems to be like a very powerful tool, right. So can there be any glitch in doing this? Remember this condition I had laid out, that when you are drawing this contour, yeah, it should not pass through any of those poles, or in fact even for that matter for the zeros, right, because that makes matters complicated. If it passes through the pole, then for one it will blow up, yeah, the value of this Fs will blow up at a pole. Even if it passes through a 0, that is also a problem, whether do you count this 0 as inside the contour or outside the contour, right, because you know that keeping tab of this pole and 0, keeping a count of that pole and 0 is what is allowing us to beautifully come up with this count of the number of closed loop poles and zeros. Now if you pass this contour through some pole and 0, yeah, then how do you count that? Do you count that as inside? Do you count that as, like when you are counting this thing here, do you count that as inside or do you count that as outside? Yeah, I mean we do not know, right. So particularly this, we are concerned with this presence of open loop poles somewhere in our contour, right, because after all the Nyquist contour we will be concerned with this open loop poles of the system. If we draw this, happen to somehow mistakenly draw this Nyquist contour, this D through some poles of the system, so some open loop poles of the system, yeah, then does it come under this count? Should it be counted as part of this or should it not? Yeah. So in order to bypass this problem, here is what is done. So think of this Nyquist contour again. What part of the contour do you think can actually give us this sort of a trouble? Yeah. You see, this infinite part of this D is generally not going to give us any trouble, yeah, because this all is, you know, at infinity. So we say in root locus analysis also we said that if you consider for all infinite poles and zeros, then it is a biproper system, of course, you know. So you say that if you have n poles and m zeros, then there are basically n minus m zeros at infinity. That is how these asymptotes go around, right. So we do not care about these infinite ones, but there is absolutely no guarantee that you will not encounter. So remember the contour here had to go through all of this, right, this entirety of this j omega axis, and in fact what I have not mentioned is, because it goes through this j omega axis, that is exactly the reason why this is a frequency domain tool. because the large part of this Nyquist, when we will see more of this when we actually take some examples and sketch the Nyquist plot, you will see that a large part of this Nyquist contour, yeah, it actually is about this plotting or mapping this j omega axis, this imaginary axis of the Argand plane, alright. That is why it is a frequency domain tool. Just like the Bode plot was about steady state analysis, we were concerned with this j omega, behavior on the j omega axis, right. So that is why it is a frequency domain tool. Now, coming back to the question at hand, suppose you have, say for example, repeated poles at the origin and some complex conjugate purely imaginary poles, yeah. Now if you try to draw this Nyquist contour, this D, you run into trouble, because if you make it pass through this one, it will blow up, yeah, that Fs part, the GC part will itself blow up, so you cannot plot this, yeah. And of course there is the other point, like whether it goes inside or outside, of course that is rendered moot under this. So what then is the way out? It turns out that there is a solution to this so called glitch. There are two ways actually. One is, let me use a different color. So one of them is, if while going like this you include this, so you take a small detour around the left of this, yeah, and around the, so yeah, this, and around the left of this like this, so you include these fellows, yeah. So this is how you modify this D, this Nyquist contour. If you happen to have open loop poles of the system that are purely imaginary or at the origin, then this is the way to do it. The other way to do it is, of course, well, you can use, what color should I use? Okay, let me use this color. The other way to do it is, you can exclude them altogether, yeah. So you choose this, yeah. So then let me draw both of them in different colors. So one way is you exclude them, as I have just shown you here. So this is going to be your chosen contour, yeah. You have this here, you exclude this here, and then you go here and then you exclude this here, yeah. You take a very small, so this is infinitesimal radius, this is basically some epsilon. This is one way, so this is to exclude. So I should probably kind of erase this part in between, yeah, it is probably creating a bit of a confusion, yeah, yeah. So let me draw this. So this is one choice, okay, and in fact we will prefer this, yeah. It is simpler because you are basically excluding this, these fellows here. So you are basically allowing marginally stable open loop systems, and you say, okay, they are still marginally stable, so let it be stable. On the other hand, if you are a stickler and you say no, if you have poles on the imaginary axis, then for certain modes, or yeah, for certain inputs, these will blow up because they will have repeated poles, and even here also you have repeated poles, then even due to initial conditions, yeah, they will tend to blow up or at least not decay. So if you think in those terms, then you should actually forbid, you should actually prevent these, you should try to avoid these, so you should actually include this, yeah. So the other idea is that, yeah, but then this is a lot of bookkeeping, yeah, so that is why we do not prefer this. So let me erase that, yeah. So what we then do is, the other choice is this, and you include the fellow here, yeah, and you will see that if you do careful bookkeeping, carefully you keep track of how these contours are being negotiated, you will still be able to draw the Nyquist diagram and correctly deduce this n, yeah, correctly deduce this n, and once you have drawn this, deduce this n, then this z can be just calculated by this, yeah. So obviously when you are including this, then this p count will consider these poles, these open loop poles as inside, yeah. On the other hand, if you are excluding them, yeah, then this p count, this pole count will exclude them, so they will not be counted as inside this contour. So that's the difference. So this excludes and this includes. Okay, so there are two ways of going about it, as I said. So with this, now we are completely ready to now start sketching some sample Nyquist diagrams for some given transfer functions and see how they actually behave, yeah, and how we can actually go about plotting these things, okay, because that is going to be of crucial importance. Understanding a tool at a theoretical level, at a technical level is one thing, but to be able to actually apply it, even maybe unaided by a computer, if you do not have this computer, yeah, at least qualitatively, can you sketch? That is a crucially important question, yeah. So that is what we shall see in the next lecture. To summarize, what we have seen today is, in this lecture, that if you carefully and cleverly choose this contour in the Argand plane and map it through this 1 plus GC, yeah, then just by looking at the number of encirclements of the origin in the 1 plus GC plane, right, you can deduce by using this simple formula, which is a consequence of the principle of argument, which I have kind of taken a little bit of time to explain. By applying this formula, you can actually count the number of closed loop poles in this forbidden region, that is this right half plane. Before we conclude, just like to add on one thing. You see, it is this 1 plus GC that we are plotting, and we are trying to find out its encirclements about this origin. So if this is my real part of 1 plus GC, and this is my imaginary part of 1 plus GC, yeah, it seems like a bit of an artificial construction, no? So ordinarily, if I am given any S, any test point on the contour, I will pass it through to S, to G and to C, and what I readily get is, immediately as soon as a test point is given, say S1, I can evaluate GS1 times CS1 immediately. This comes directly, yeah. Now in order to get 1 plus GC, then I am required to add 1 to it, yeah. Now this is where I take a bit of an exception to. Why should I do this? Yeah, I mean, open loop wise it does not make much sense, no. It is just that this rule tells us that this 1 plus GC is giving us this this closed loop transfer functions poles, yeah, the closed loop poles, the zeros of 1 plus GC is giving us this poles. So that is why we are having to do this. But if you think of it from a plotting perspective, what am I doing? I am given some S1, I am passing it through G and C, and I am taking the product of GS1 and CS1, then I am adding to it 1, and then I am plotting this point somewhere here, yeah. But before adding this 1, yeah, I was probably somewhere here, yeah. So this is basically GC, and this blue fellow is something like GC plus 1. Now the point is, do I really need to add this 1? You see, if I draw now this GC plane, instead of this GC plus 1, GC and this imaginary part of GC, yeah, now everything is shifted by something to the left, by 1 exactly to the left. So now, instead of, I mean, if I try to draw this on the same plot here, you see, then this would be, this green fellow would be my imaginary part of GC, yeah. So this would be my imaginary part, and this would be the real part, yeah. You see, this is after all just a real shift, no. So it is the imaginary axis that gets shifted. The imaginary part does not get affected by the addition of this 1, yeah. So essentially what I am saying is that instead of looking at this origin of this here, yeah, sorry, I drew that incorrectly. So this yeah. So if I want to draw this on the GC plane, yeah, I would basically have this here, yeah, somewhere here, right. So now instead of looking at this origin of this 1 plus GC plane, let me look at the minus 1 plus J0 point on the GC plane, right, because if I do that, that is tantamount to the origin. Yeah, on the GC plane, the minus 1 plus J0 point is tantamount to the origin of the 1 plus GC plane, yeah. So that is why now instead of putting this condition like this, that net counterclockwise encirclements of the origin in the 1 plus GC plane, what people say is that n, the net counterclockwise encirclements of minus 1 plus J0 in the GC plane, yeah, is equal to P minus Z. So instead of, while plotting, instead of artificially adding this 1, yeah, to get this GC plus 1 here, right, what I then do is I just look at the GC, do not add this 1 to it, but instead of counting the encirclements about the origin, I count the encirclements about the minus 1 plus J0 point here, right. So that is the important bit. We will take off from here and we will take some examples in the next lecture which will make things a lot clearer.